welcome to this 38th class in our course the physics of materials. So today we are going to look at the phenomenon of superconductivity and try to pull together some of the first of all understand what it is, get a feel for what is this phenomenon, what are its features, and then also try to understand, see if there is get a feel for the theory that has helped try and explain this phenomenon. Okay, so that is what we will do. So the phenomenon is simply called superconductivity. Okay, basically what it is that if you take the resistivity rho, resistivity of materials rho, and plot it as a function of temperature. Okay, so people have done this. We have already seen temperature dependence of resistivity of metals and so on. In general, as you raise the temperature, resistance goes up. So as you raise the temperature, resistance goes up. So this is sort of the trend that you see. Now for most metals, if you keep lowering the temperature, so this is going to keep coming down and then eventually it will level off at some value very close to 0 Kelvin. As you keep getting closer and closer to 0 Kelvin, it will reach something like that. Okay, so we will assume that this is 0 Kelvin, 0 Kelvin, this is Kelvin. So temperature in Kelvin and this is 0 Kelvin. So as you approach absolute 0, the resistivity of the material keeps decreasing and then it eventually levels off at some value. Okay, so this is what is seen for most metallic systems. If you investigate it, you will find this. Now it turns out that for some systems what you see is, you see the same trend, resistance is decreasing with temperature, then at some particular temperature the resistance abruptly drops to virtually 0 and stays there all the way as you go down in temperature. Okay. So you see, so this is a normal metal, and materials which show you this behavior where resistance is decreasing up to some point, then abruptly it drops to virtually 0 resistivity and then it stays there. This kind of a behavior is the materials that display this kind of a behavior are called superconductors. Okay, so these are called superconductors. So and as a result, and that is mainly because as the name suggests, once you get past this temperature, once you get below this temperature, you can conduct electricity with virtually no resistive losses. Okay, so this is virtually 0. It is more than it's many orders of magnitude, 13 orders of magnitude or even better than what you would ever get there, and it virtually drops to 0. So that is the state at which you find this material. Superconductivity as a phenomenon was discovered in around the year 1911 and is credited to Kimmerling Onnes. So it was discovered in 1911 and it was discovered in mercury. Okay, the metal mercury, if you keep lowering its temperature, this phenomenon was discovered, that once you cross some temperature, abruptly resistance dropped to 0. This temperature is called the critical temperature, T subscript C. T subscript C is what it is referred to, and it is T subscript C is the critical temperature. Okay, so this is critical temperature and it represents the temperature that you have to go below for you to get the superconducting stage, and if you cross this temperature you get the normal conductivity, material remains conducting the way you would normally see a metal conduct electricity. So this is the basic framework within which superconductivity was discovered, and as you can see, if you have a material which has virtually 0 resistance, the technological uses for it are tremendous. Okay, so that is something, and that is the reason why since the time it was discovered, a lot of effort has been spent researching this class of materials or this type of materials to understand what is superconductivity, what is the phenomenon, what are the factors that control it, and in fact the dream has always been that you will get a material that behaves like a superconductor at room temperature, that is the dream. But actually as you can see, this is something that as it was even as it was discovered very close to 0 Kelvin. Okay, so we are talking of just a few degrees past 0 Kelvin that this was discovered. That is not a temperature that is easy to attain. It is very expensive to attain that temperature and maintain that temperature. So you are actually, it is a very difficult process to stay at that temperature, and an expensive process. So therefore in the form that it was originally discovered, practical usage was going to be difficult except in specialized cases. So since then it has been seen that of the order of various materials were then investigated to see if you could see the phenomenon of observe the phenomenon of superconductivity in them, and it turns out that something like 28 metals display superconductivity, and usually this is occurring at temperatures less than about 10 Kelvin. Okay, so all of these metals in their elemental state are showing you superconductivity at temperatures less than 10 Kelvin. So that is what you see. Then there are several intermetallic compounds and alloys that show superconductivity in the temperature range in temperature less than about 20 Kelvin. Okay, so temperature less than 20 Kelvin is sort of what you are looking at for most of these systems. So this is very so this is all minus 250 degrees C, that is what you are looking at, or even less, minus 253 degrees C and lower. So that is not something that is easily attained. You need typically you would be using something like liquid helium to get to those kinds of temperatures. So this was seen. And so you can see that since its discovery, more and more materials have been discovered which show you this phenomenon of superconductivity, and more recently in the year 1986 a new class of materials were discovered which were actually ceramic type of materials, which by the way incidentally at room temperature are going to be insulators. Okay, so they are ceramic, so at room temperature they are insulators, but if you lower their temperature they go the opposite way, they do not just become conductors, they become superconductors. Okay, and in fact so ceramic type of materials were discovered, lanthanum barium copper oxide, yttrium barium copper oxide and so on, which basically had of the order of say 90 Kelvin as the temperature T sub C. Okay, so so this is the kind of temperature you can start seeing, and when you start looking at these kinds of temperatures, they are materials which can then be cooled to these temperatures using say liquid nitrogen, which is much easier to handle. Okay, so that is the basic idea that so when you get to the 90 Kelvin 100 Kelvin range, you can start reaching that temperature with liquid nitrogen. So but of course these are ceramic materials, so they are very difficult to process. So if you want to make something technological out of it where you want long wires and so on, this is going to be very brittle. Okay, so it is not a very convenient thing to work with. So experimentally this is what has been done, and so experimentally a lot of people have worked with these materials, investigated a variety of materials to see if they are superconducting. They have tried to come up with new configurations of materials which may be superconducting. Some of these discoveries have been accidental, some of them have been very well planned and systematically encountered and so on, and so this is the state of affairs. Additionally, people also investigated the various features associated with a material that is showing you superconducting behavior. Okay, so what was seen is, of course, as you can see right here, temperature was had a very important role to play. In other words, if you crossed a certain temperature, you broke down the superconducting stage, right? So you have a superconducting state. You raise the temperature, you cross some temperature threshold, you break down the superconducting state, and so therefore raising temperature is in some way opposing the superconducting state. So in the same form, when they looked at all the parameters that would impact the superconducting state, they found the following. If you take a superconductor and you send current through it, okay, you send current through it, you can keep increasing the amount of current you send in it, okay. So and effectively we would quantify that using by looking at the current density that you are sending through the material. So you can keep raising the current density that goes through the material, and what is found is that once you cross a certain current density, again the superconducting state breaks down. So it remains superconducting till you reach a certain current density, then it breaks down. Also similarly, you can take a superconductor and place it in the presence of an externally applied magnetic field, okay, and in the presence of an externally applied magnetic field, it will continue to remain superconducting. You keep increasing the field. So we spoke of magnetic fields. We basically had said that is the externally applied field is a field that we would designate as H. So you can increase H, okay. So amperes per meter. So you keep increasing H, then you will reach a certain value of magnetic field imposed on that material when suddenly the superconductivity breaks down, okay. So there are three things that can break down the superconducting state: high temperature, high current density, and a high magnetic field. So these are three things that can break down the superconducting state. So in fact what we normally do, I mean, you can just plot it like this. So this is temperature axis, this is the magnetic field axis, applied magnetic field, and then the current density J. So if you have no current flowing through it, or virtually no current flowing through it, and no field applied, you find that as you raise the temperature, you cross this T subscript C, or in the parlance of people who use this material, they just say T sub C, so to speak. So once you cross the critical temperature, the material stops being superconducting. Similarly, if you keep it even at very close to 0 Kelvin and you keep raising the field that you have applied at some particular field H subscript C, the material stops being superconducting. Similarly, with no applied field and very low temperature, if you raise the current density at some particular current, you cross some current density and you lose the superconducting behavior, right. So what is actually seen is you have a range of combination of all these. So within this from the origin till you reach, there is some surface that you can think of which consists of current density values, the field values, and the temperature values. Within that surface, as you go below that surface towards the origin, you have a range of combination of conditions under which the material continues to remain superconducting, okay. So this is a very fundamental piece of information that you can obtain for a superconductor, this kind of a behavior, and originally this was obtained. So so trying to understand superconductivity would require us to come up with theories which would then help explain what is happening on the other side of the boundary, what is happening this side of the boundary. So that is the basic thing that people working in this area have tried to explain. Now what is seen in fact with respect to the magnetic field, okay, with respect to the magnetic field, what was seen is that when you take a superconductor and you apply a magnetic field around, you place it in the presence of a magnetic field, it is seen that the superconductor completely excludes that magnetic field. It does not permit the magnetic field lines to enter it, okay. So it excludes the magnetic field. So and that phenomenon is known as the Meissner effect. The Meissner effect refers to the fact that a superconductor opposes a magnetic field, okay, which is not the case actually with a normal conductor. A superconductor opposes a magnetic field. Now this is considered a very important effect that was discovered about superconductors, because it clearly says the fact that this Meissner effect exists for a superconductor indicates that a superconductor is not simply an exceptionally good conductor, okay. In other words, if you take a very good conductor, the theories for a conductor are such that if you take a very good conductor and hypothetically you find ways in which you can reduce its resistance, it will still not display the Meissner effect. The Meissner effect is such that it's somewhat different. It is ensuring that no matter when or how the magnetic field is applied, the material will exclude that magnetic field. So in other words, something so it tells us two things. First is that the material that is showing you superconductivity is doing so using a mechanism that is not the same as a normal conductor. Okay, so that is why it is not simply a very good normal conductor, because characteristically it is doing things that are different from a normal conductor. And importantly, that magnetism opposes superconductivity. Okay, magnetism opposes superconductivity. So something about what magnetism requires of a material is opposed to what superconductivity requires of the material. So this is a very important idea to identify and grasp of the superconductor. So something that magnetism requires of the material is opposed by what superconductivity requires of the material, or vice versa. Something that superconductivity requires to sustain itself is being opposed by what the magnetism requires of it. Okay. We will also note that having stated this, if you actually look at the kinds of materials, for example I said ceramic materials, certain ceramic materials have show you superconductivity at relatively high temperatures. They are in fact called high temperature superconductors, and that is a little bit misleading, because normally in the conventional sense when you talk of high temperature you are talking of 1000 degrees C, 2000 degrees C and so on. This is not at all in that scale. This so called high temperature superconductor is not even at room temperature, it is at much lower than room temperature. In fact it is of the order of minus 200 degrees C is where it is superconducting, or of that or minus 190 degrees C, let us say minus 190 degrees C is where it is superconducting. It is only a high temperature superconductor relative to the fact that the original superconductors were discovered at showing superconductivity even at much lower temperatures than that. Okay, so where you are talking of in Kelvin scale, where you are talking of about 100 Kelvin temperature for a high temperature superconductor, the original superconductors which are low temperature superconductors were less than 10 Kelvin. So in that relative sense it is a high temperature superconductor, it is not even at room temperature. Okay, so we definitely need some amount of cooling. As of today the materials in which superconductivity has been discovered are such that you definitely need some cooling to have this superconducting state. So anyway, so you have this theory that, I mean this indication that magnetism opposes superconductivity, right. So that is a very important piece of information. So attempts were made to try and see if there is a manner in which you can explain what is going on in the material and see if you can understand why or how the material is beginning to show a superconducting state. So the most successful attempt is what is now the accepted theory for superconductivity, and that is attributed to 3 people, BCS. So this is Bardeen, Cooper and Schrieffer. Bardeen, Cooper and Schrieffer, they came up with a theory that helped explain superconductivity. Still it only explains superconductivity for the original set of materials where the temperature, the critical temperature was of the order of a few Kelvin. Okay, so this theory for example is unable to explain how a material at say 90 Kelvin or 100 Kelvin or thereabouts can show you superconductivity. Okay, so therefore this even at this stage, even though this has successfully explained low temperature superconductivity, there is still no accepted theory that explains high temperature superconductivity convincingly. So that is the state it is in, and the way they explained it is that they said in terms of a theory, they theorized that there were pairs of electrons that sort of operated in a coordinated way. Okay, and these pairs of electrons were attributed, this idea was attributed to Cooper, so they are called Cooper pairs. And it requires the electrons to have opposite spins and opposite k vectors. Okay, so the pairs of electrons would have opposite spins and opposite k vectors, and as a result of opposite spins it would as a result of this combination it would appear as though the net k vector was 0 and the net spin was 0. Okay, so suddenly from electron, which is a half spin half integer spin particle, we are having some kind of a composite particle. You can imagine it as some kind of a composite particle which is operating as this pair, where the taken together their net spin is now an integer spin. So what was a half integer spin suddenly becomes an integer spin. Okay, so what was half becomes 0, plus or minus half becomes 0. The important thing about this is that when you go from half to 0, the qualitative difference, the specific difference that comes in is that when it is a half spin particle, it follows the Fermi-Dirac statistics, which is what we have discussed in great detail early on. Okay, and for a particle to qualify as a fermion, so that it follows these Fermi-Dirac statistics, the requirement is that the spin should be a half integer spin, which is what is true for an electron. But when you take a pair of electrons, especially a pair of this sort where the spins are opposed to each other, and the net spin for that then looks like a 0 spin, it has suddenly become an integer spin particle. Okay, so it behaves like an integer spin particle if they are really coordinated, if they really have linked up with each other in some fundamental sense. So then it behaves like an integer spin particle, at which point the statistical behavior of the set of particles changes. Okay, so that from being a fermion, the Cooper pair, so an individual electron is a fermion, and it follows Fermi-Dirac statistics, but a Cooper pair of electrons which now has an integer spin behaves like a set of particles which are called bosons. Okay, in the next class we will look in greater detail about bosons, which is and they are a set of particles just the way fermions are particles which follow Fermi-Dirac statistics. And therefore, I mean they are the people Fermi, Enrico Fermi and Paul Dirac are credited with that distribution and the use of that distribution, so to speak. The the bosons are credited to Satyendranath Bose and Einstein. Together they proposed it, and so that is and they are, and in honor of Satyendranath Bose, the name boson is given. Okay. In fact, he was the one who originally proposed it. There was some reluctance to accept it. Einstein supported him and actually showed that there was something more fundamental that could be said about those particles, and so they became bosons, and that only then they got accepted. So electrons behave like fermions. The Cooper pair of electrons behaves like bosons, because suddenly what was a half integer spin has become an integer spin, and bosons are particles which require integer spin. Okay. As I mentioned in the last class, what we think of as light, photons, are bosons. I mean they have all the characteristics required to be a boson. The lattice waves the waves in a lattice which are called phonons, they are also bosons. Okay, so we suddenly see that you have a number of particles that we are in fact photons certainly we have been used to before, and they are bosons, and there are two other things that we have just discussed which are bosons. Now the interesting thing is, and that is why we will actually look at Bose-Einstein statistics in greater detail in the next class. There are two things that are interesting. This Cooper pair of electrons actually in terms of a distance, it is not that they are very close. That is the very interesting thing about this Cooper pair. This Cooper pair can actually be a pair of electrons which can be relatively far apart, okay, but they interact through the lattice with each other, okay, and therefore maintain their state. They actually, what happens is there is a certain energy associated, a certain decrease in energy associated with the formation of this Cooper pair, and once that pair is formed, they actually maintain that state. They maintain that state, and you have to provide enough energy to break that state. You have to break that Cooper pair before they start behaving like electrons before. Okay, so they sort of condense into this state. They condense into this state of wherein they are in this paired state, and because they are paired with each other, they sort of in this condensed state they avoid the interactions with the lattice, or they are somewhat impervious to the interactions with the rest of the I'm sorry, with impervious to the scattering events that normally the electrons are prone to. they tend to be relatively far. So if you actually see, atomic distances are of the order of angstroms, these could be of the order of several nanometers apart these electrons could be, and they would still continue in a coordinated way, and therefore in a certain length scale you may actually have several Cooper pairs which are sort of within that length scale, okay. So confined to the same length scale. So Cooper pairs are of that sort, and interestingly they themselves are bosons. On top of it they interact with each other. The fact that they are, it's a long range phenomenon, so to speak, they are interacting through in this long range using lattice vibrations, okay. So therefore they are bosons, and they use phonons to interact with each other, which are also bosons. So you actually have two sets of bosons existing there which are interacting with each other. The particles themselves together are represent a boson kind of behavior, and they are interacting with each other, they are sustaining themselves by interacting with each other using phonons which are also bosons. So you see, for a multiple in a multiple sense you get this boson phenomenon here, and that is the reason why we will look at it in a little greater detail in the next class. And also one of the characteristics of the bosons is that at very low temperatures they form something called the Bose-Einstein condensate, okay. So these are also some forms of these also are essentially condensing into a condensate there, and so in the next class we will look at the Bose-Einstein statistics, and we will also look at the Bose-Einstein condensate, okay. So Cooper pairs are formed. So the theory says that there are Cooper pairs of electrons which have opposite spins, opposite k vectors, so they behave as though they have no net spin and no net k vector, and they are bosons. They avoid lot of the scattering events in the material, and they are able to they have a certain distance associated with them, and so they are able to travel along through the system. And as you raise the temperature, if you provide enough energy, you break down this pair, and that is when the superconducting state suddenly fails. But importantly, all these ideas trace themselves back to the Meissner effect. And the Meissner effect, and that is the reason why we say that the Meissner effect is such an important effect in trying to understand superconductivity. See, the Meissner effect basically says that the discovery of the Meissner effect conveyed the idea that magnetism is in some fundamental sense opposed to superconductivity. So what is it that magnetism requires of the material? Magnetism requires that the electrons align themselves in certain way, so that the magnetic moments of the electrons align themselves. So therefore the spins of the electrons would have to align themselves, right. So you have randomly oriented spins, you suddenly want them all oriented in one direction, so that you get the magnetic moment in that direction. So when you say that the alignment of electrons is what magnetism brings to the material, or tries to enforce on the material, the fact that alignment is disrupting superconductivity, okay. The fact that the alignment is disrupting superconductivity suggests that the superconductivity state requires the opposite, okay. So that is a very important thing. To repeat it, the magnetism will require spins of electrons to align themselves, so that you get the magnetic moment in one particular direction. So if you say that magnetism is somehow interfering with superconductivity, and that if you raise the magnetic field strength you break down superconductivity, it conveys the idea that the aligning of spins is something that is not desired in the superconducting state, which can be taken one step forward to say that perhaps deliberately aligning them in the opposite way is what superconductivity requires, and that is what is captured in this Cooper pair. The fact that this Cooper pair takes in electrons of opposite spins, okay. So that is how this and that is why the Meissner effect is not simply some interesting experiment interesting but an aside, so to speak, of superconductivity, but it is a very fundamental aspect of superconductivity, and it is in that sense that it captures this basic idea of superconductivity and tells you that it is something that is different from a normal conductor. In a normal conductor we are not talking of pairing up of electrons of opposite spin and so on, so the electrons are all independently running around, so this entire process is not required for a normal conduction process, okay. So only for a superconducting state we seem to require all of these additional information, okay. So so they have received a Nobel Prize for this for their theory on the of superconductivity. I believe it is a 1972 Nobel Prize that they got for their work to explain superconductivity. We just discussed that magnetism is opposed to superconductivity and vice versa, and that they actually and therefore as you raise the magnetic field eventually the superconducting state breaks down. In this context there are actually two types of superconductors, they are simply called type 1 superconductor and type 2 superconductor. So there is a type 1 superconductor and a type 2 superconductor. The difference is simply this, in a type 1 superconductor what we just described is how the system behaves, that is you raise the magnetic field that the superconductor is experiencing, when you cross some threshold the superconducting state suddenly fails. Okay. So in fact we use the terminology S state and N state. So this is the superconducting state, and the N state is the normal state. Okay. So in a type 1 superconductor, when it is in the superconducting state, when you are below that critical field, when you are below the critical field H in some critical field, it is entirely the entire material is in the superconducting state. Okay. So there is no so it is only in one state, it is entirely in superconducting state, and when the superconductivity breaks down, it does so kind of abruptly, and then everything becomes the normal state, the entire material becomes normal state. Okay. And so the S-N transition occurs at the critical field that you have applied, H sub c, critical magnetic field. At the moment we are not talking of the electric field or the temperature, so it occurs at this temperature. In a type 2 semiconductor, the SN transition is not abrupt. Okay, so that is a significant difference, the SN transition is not abrupt. So you have the S state, the superconducting state, and the N state which is the normal state, but in between there is a mixed state. Okay, so in which what is happening is there are regions in the material which are superconducting and regions in the material which are normal conductors. So there is a mix of superconducting state material within the system and normal conducting state within the system, and then as you keep increasing the field, slowly the normal conducting state becomes more and more and more, and eventually it completely becomes a normal conductor, you lose complete superconductivity in the material. Okay. So that is how you have it. So for a type 2, so this is type 1. For type 2 you have so SN transition is gradual, so here it occurs abruptly, SN transition is gradual, and so you actually have a H C subscript C subscript 1 and a H subscript C subscript 2. So you have to cross H sub C before the normal state begins to appear in the system, and then if you continue you will have to cross H subscript C subscript 2, HC2, HC1 you will cross, then it starts getting into the mixed state. Between HC1 and HC2 it remains in the mixed state. If you go past HC2 it becomes a normal conductor. Okay, so this is how it is occurring, it is gradual. The advantage though is in some usages the type 2 semiconductor becomes preferable because you can handle much higher fields. Okay, so that is the reason why sometimes type 2 semiconductor may become preferred. Okay, so in that sense there is some variation in the even within the superconductors you have this variation in the type of superconductivity that may be present within the material, and therefore you have different classes of material which are either type 1 or type 2. Okay, so if it is a type 1 you will only have a HC, whereas if it is a type 2 you will have a HC1 and a HC2. So that is the difference between them. Now in terms of relating to what we have learnt, what we have to understand is that we are looking at, see, one of the problems with this which is how the whole BCS theory actually was considered a very significant contribution. One of the problems with this situation is that the temperature at which this, or when the original set of superconductors were discovered, the fact that a state of matter or a particular state that it was existing in, superconducting state, broke down at in the order of about 5 to 10 Kelvin, that is the temperature range at which it broke down. That meant the energy difference that it see, obviously it means that there is some state that is existing in the material which is a lower energy state, right. So that is why it is getting into that lower energy state. As you are cooling the system, there is some lower energy state the system is able to attain, it is able to get into that lower energy state and it stays there. And as you raise the temperature, you are adding more and more energy to the system. When you put in just the amount of energy difference between that lowest energy state and the next state, it breaks down this lower energy state and you start getting the normal system, normal material. Now the fact that it is in the 10 Kelvin range or less implies that the energy required for breaking down that state is very small, okay, relatively speaking. So that was the problem, because if you look at our systems, when you say that the electrons participating in conduction and so on are all sitting near the Fermi surface, and that is what is really doing all this work. The Fermi surface relatively speaking is a relatively large amount of energy. So you have to find ways in which electrons sitting at the Fermi surface can attain a state which is a very where the difference in their energy levels from their original state and this state is a very small energy level, and that is where this Cooper pair concept really helped address a lot of those issues in trying to explain something where the energy relative amounts of energy that people had to account for were very small. Okay, so that is why this is important. Now in terms of usage, it is superconductors have not really have not really penetrated normal common day to day usage, okay, and mainly because of the cost involved in making the material, cost involved in and especially even the so called high temperature superconductors are still at a relatively low temperature operation. So therefore in terms of operating the superconductor, it is not an easy thing, and on top of it these are and therefore if it is a ceramic material also it is a brittle material. So these are all the issues that are involved in its usage. So therefore it is not really penetrated the more common places where you may expect a very good conductor to exist. However, there are a lot of specialized uses for which superconductors are necessary and have therefore found a lot of utility. The first one is of course is in the medical devices or medical equipment. So for example, your MRI scans, magnetic resonance imaging scans, are places where superconductors are used. Okay, so MRI scans use superconductors. The reason being, for an MRI scan to work, they need a very high intense magnetic field. To have a very intense magnetic field, you have to if you are using an electromagnet to generate that intense magnetic field, you have to flow very high currents through those electromagnets. Okay, so you have to flow extremely high currents through those electromagnets to get the kinds of fields necessary for you to do MRI imaging. Now if you use a normal conductor, no matter how low its resistivity, if you use a normal conductor, when you flow higher and higher amounts of current, it is going to generate a lot of heat. In fact, most normal conductors, if you use the kind of currents that an MRI scan might use, you are actually going to sort of you are very likely to even melt the material. That is the amount of heat that you will generate by forcing that amount of current through those wires. You will have to put a lot of voltage to send that kind of current through those wires. So therefore normal conductors are not convenient, are simply not capable of doing the job of an MRI of doing the job that is required of them to create the magnetic fields in the electromagnets in an MRI equipment. Superconductors are able to do that. So and this is also a specialized equipment, so you can afford to have equipment of this sort using expensive material. There are I mean at least in a relative sense, and therefore this has actually become successful. You find MRI scans quite commonly available in various hospitals and so on. So this is one place where you use such superconductors. There is another place where you use it again for mainly from the perspective more than mainly to take enough current so that you can generate a magnetic field. Okay, so that is the general place where you are using it. It is not simply to carry high currents. It is not simply just to carry a high current between point A and point B. It is more that by carrying this current in the form of a coil or some such thing, you can create very high magnetic fields. Okay, so that is the basic place where this is used. So this is actually used in particle accelerators. Okay. Particle accelerators where you need intense magnetic fields use superconductors. In fact, a very major part of their engineering and so on is to have coils made out of superconductors, so that they can get the magnetic fields that they desire. So in fact, at the time of recording this lecture, if you know the at CERN, they are working with a particle accelerator, specifically looking for basically they accelerate the particles and they smash them together, and so that they can look at the debris of that collision and see if they can understand what are the more fundamental constituents of those particles. So there they are working on a particular particle which is called the Higgs boson. Okay. So they are looking for a particular particle which theory has predicted or theory claims it might exist, called the Higgs boson, and the only way they can find out whether or not such a particle exists is to do these accelerated tests where I mean these tests where particles which have been accelerated in very significant sense are smashed together, and then in the debris they look for the what is the constituents. The expectation is that if you have high enough energy, you will get this you are likely to see this boson, and so it is interesting to see here that this particle which they are searching for is a boson. Okay. So it meets all the requirements to be a Bose-Einstein particle, a boson, and to do that you are using Cooper pairs, which so to look for it you are using a superconductor where the Cooper pair of electrons operates like a boson, and it uses phonons to interact with each other, which is also a boson. So at some fundamental level you are using two bosons to search for a third boson, if you want to look at it that way. Okay. Of course, it is not as simply stated, it is not as simple as I have stated it, but that is the basic idea. In the system that you have, you are using two bosons to search for a third boson. So basically, and so I think you can see here that it is in this context that we will actually look more carefully at what a Bose-Einstein material is, what are these bosons, and what can be said about them in greater detail in our next class. So so this is another area where a superconductor is used. So it is used in medical equipment and it is used in particle accelerators. In both of these cases, as I mentioned, it is not simply the fact that it can hold high current or that it can carry high current between point A and point B. It is because that you actually have to you can generate very high magnetic fields with it. Still, cooling is a very big issue here. So from a technological perspective, when you look at superconductors, cooling still remains a major issue, and it is also it is something that you have to control in a very careful way. So for example, in the particle accelerators, when you are saying that when you say you are going to operate your system at say 2 Kelvin, okay, so 2 Kelvin is something that is very close to absolute 0, 2 Kelvin, okay. That is actually a big technological challenge. You have a massive piece of equipment, a very significant fraction of it has to sit at 2 Kelvin. It is a big challenge because even if something goes wrong, you cannot cycle from 2 Kelvin to room temperature and back to 2 Kelvin quickly. Okay, it may take several weeks for you to very gradually raise the temperature of the system, whichever is the affected system, to room temperature, so that you can attend to it, okay, and then very gradually lower the temperature. So just attaining the temperature and coming back from the temperature to room temperature or going back to the temperature is it has to be a very gradual process, otherwise you will create a thermal shock. Okay, so this has to be done very carefully. So there are a lot of in addition to the fact that it is at low temperature, simply reaching that temperature and maintaining that temperature is something that has to be done in a very controlled way. Okay, so therefore even in that sense there is a technological challenge in using in working with superconducting materials. Okay, and as I mentioned, and so it has already percolated into certain types of activities, and those are at least 2 examples are out here, but it has still got some ways to go before you can expect to before you can consider a possibility that it might pervade all normal usages of materials. As a technological accomplishment or a dream, it is certainly a very good thing to aim for, that you could have a material that is perhaps superconducting at a much higher temperature and possibly even at room temperature. but we do not know if there is a theoretical limit to the superconductor. We do not know if you may that there is a fundamental reason why you may never have a superconductor at room temperature. Those things are not really known. Okay, and in that sense, in fact, even the as I mentioned, the Bardeen BCS theory, the Bardeen-Schreiber-Cooper theory, is still something that only explains the low temperature superconductivity. In fact, based on this process that they have explained, they expect that the superconducting state has to break down around 10 Kelvin or so, or at some low temperature of that order. Okay, so if something is showing you superconductivity at 100 Kelvin, it is fundamentally not using this. I mean, it is fundamentally not going on the basis of what this theory is suggesting. So there is still scope to understand superconductivity in the sense that there may be something much more fundamental which explains superconductivity, which may either augment the BCS theory or may even replace the BCS theory, but in principle the BCS theory is the fundamental theory that explains superconductivity. In terms of technological challenges, as I mentioned, yttrium barium copper oxide, in fact they will say YBCO is how it is typically mentioned, but it is actually yttrium barium copper and oxide. Okay, so this is 37 is what I remember. So this is yttrium barium copper oxide. So these are the kinds of ceramic materials with which you can get superconductivity at higher temperatures, and in this case what is complicated about this kind of material is you have to get a particular phase which may have a particular crystal structure and so on. So to get these materials in large quantities, and in dimensions that are useful, meaning in the form of a wire or in the form of a tape. Okay, so in the form of a wire or in the form of a tape, to either get it in large quantities or in dimensions that are useful, and if it is a wire or a tape, you want it to be a continuous wire or a tape. It does not help, if ever so often you have to make a joint and perhaps the joint is made out of some other material, that does not work. You have to have something continuous. Okay, so only then you can have it working. So the challenge is to make it in large quantities and in dimensions that are useful. This is not an easy challenge because it is a ceramic material. You cannot just form a block of it and then start post processing it to get this material. You have to sort of make it in the shape that you wish. Okay, so that is how it is. So this is a challenge, and so a lot of people work on this. Okay, so but at the same time, as I mentioned, already specific usages have already occurred and people are using it. Okay, so to summarize, what we see is that today we have looked at the concept of superconductivity. We have looked at several of the key aspects associated with it. For example, the fact that it has a critical temperature T sub c, it has a critical current density J sub c. Okay, so where if you cross that current density, you will break down the superconducting state, and it has a critical field associated with it, where if you cross that particular field, the superconducting state will break down. For every given superconducting material, you can create you can identify these three parameters: the H sub c, the J sub c, and the T sub c, and that will then give you the envelope within which you have to operate to keep it in the superconducting state. Okay, so this is the fundamental aspect of a superconductor. As I mentioned, of the three, the temperature and the current, more than the temperature and the current, it is the effect of the magnetic field on the superconducting behavior that formed the basis of trying to come up with a theory for understanding superconductivity. The effect of the magnetic field on the superconductor was something that had been explored in great detail by Meissner, and hence it was called the Meissner effect. And so the first successful theory in explaining superconductivity really focused on taking advantage of the Meissner effect to explain the superconducting behavior. That first successful theory, as we saw, was the BCS theory, or the Bardeen-Schreiber-Cooper theory. However, I have also indicated to you that it is not something that explains all of superconductivity as we know it today. There are still aspects of superconductivity that are not explained. Okay, and in terms of utility, already several specific utility of superconductivity is already there. It is already there as a commercial device. There are many places that you can actually utilize superconductivity. It is there both as a commercial device that common people can use in the form of these MRI equipment, and it is also still there in highly sophisticated equipment such as the particle accelerators, which are the few particle accelerators that you see around the world, okay, which are by themselves very complex engineering equipment, okay. And in principle the in a fundamental sense the superconducting theory requires the use of bosons, both in the form of Cooper pairs, which are bosons, and in terms of the phonons that are used for the Cooper pairs to sort of communicate with each other, and it is that coordinated movement of those two electrons that enables them to avoid getting scattered by all the other phenomena that exist, the normal scattering phenomena that electrons face, okay. So this is the layout of the basic ideas of superconductivity. So with this we will halt today. We will in the next class, as I mentioned, we will look exclusively, since we have encountered bosons now on 3 different levels, on a few different levels in fact, in the form of photons, phonons, and also the Cooper pairs. 3 levels we have looked at bosons, and I also mentioned that they are using it to search for the Higgs boson. We will look more carefully at the Bose-Einstein statistics because it seems to impact the way some of the material behavior happens. So next class we will look at Bose-Einstein statistics in great detail, plus also some peculiarities of the Bose-Einstein statistics, certain special predictions that it makes, and what has happened with respect to those predictions. So this will be the main idea that we will explore in our next class. So with this we will halt for today, and we will take it up in our next class. Thank you.